So Professor Saikat Ghosh from IIT Kanpur, and he is going to talk about magnetometers, atomic magnetometers. So Professor Ghosh.
Yeah, thank you, Subhadeep, for being the convener of this beautiful school and also introducing. But I should say, firstly, what Anil had started with the apology that, like me being one of the organizers, it's always kind of strange to think of actually giving a talk. And secondly, everyone must be tired. I'm also very tired. It's like end of the week, Friday, 6 to 7. It's really a difficult time. And also I have 1 hour, and I was really oscillating between whether to actually have a talk where I should just talk of introduction to atomic magnetometry, or the way we got into atomic magnetometry over last couple of years by actually doing an experiment and trying to understand how, can you hear me? How well actually this thing works as a magnetometer. So I kind of chose a hodgepodge of that, and as a result, I don't know, like whatever, how much I can cover, I'll do that. Few things I'll try to go a little bit in details, but this will be basically kind of very simple back of the envelope experimentalist way of thinking about things and the most basic things that we have been concerned about. And actually this lecture is partially magnetometers in a standard sense and how to think of them as an experimentalist, but also partially this memory, atomic memories. So actually it's like a combination of two things coming together, and I'll try to argue that, like there might be sufficient interest to think of atomic memories as good magnetometers, or at least that's how we are looking at. So to start with, since this is a short time, so just the few references. So these are like 2 excellent books already written in magnetometry. It's a huge field over almost like 80 years or so on going on, and both the books are actually are very detailed. And of course, one of the authorities in this field, Professor Dimitri Butker, actually will be here with us next week. He himself will be giving some talks, so many of these questions you can just go to him. And for atomic memory, this book by Professor Girish Agarwal, actually it's titled Quantum Optics, but it talks a lot about the physics that I'll be talking about. And of course, this review of modern physics, it's kind of interesting that Polzik's group had simultaneously worked on quantum enhanced precision and magnetometry partially, but also on atomic memory. So actually some of his languages, some of the language used in this review of modern physics is kind of common to both. So with that, and just a quick motivation for why atomic magnetometers, in some ways, this is a slide taken, this is a thing taken from Wikipedia, and you can actually see that kind of the state-of-the-art commercial things, or rather like things that are kind of out in the field, are at the level of attotesla, and these are all like these records. Ones are actually taken with, are held by squid magnetometers, which are actually a flux gate magnetometer. So it's not directly measuring the spin as opposed to atoms, but nevertheless their sensitivities are mind-blowing, and there are enough reason, already in Amar's talk we have heard, and hopefully like on Monday itself we'll hear a lot of fundamental physics reasons and technical, human brain imaging and so on, why magnetometry is interesting. I think this crowd, I don't need to motivate that. But just kind of where atomic magnetometers are, if you see, this is kind of the magnetometers that are around, and atomic magnetometers are very close to squids in terms of sensitivity, and the question is whether really atomic magnetometers can be taken to attotesla kind of sensitivity, so that like it actually becomes kind of the dominant one. This is a cartoon taken from this article where actually see that in terms of sensitivity, the scale is sensitivity, atomic magnetometer is very close to squids, but actually if one starts talking of how you can miniaturize, there actually atomic magnetometer starts winning. You can bring these magnetometers very close to the sample. This is an image of actually brain imaging with a squid magnetometers versus atomic magnetometers, where actually you see this, it actually can be made very small. Though today I'll be talking a little about like cold atom magnetometers, but let's just get started. So these are like very basic things, particularly for a lot of experimentalist students in the lab, something so that we can remember how to think of the sensitivity and what are the factors that go in. So the very basics is basically there are few ingredients. The primary ingredient is optical field, and then spins. And there are two kinds of physics that goes on. There's a magnetic dipole interacting with magnetic field. Of course, those are the sensors. So there's a part which is the dipole Hamiltonian, magnetic dipole Hamiltonian. But there's another part, which is the light matter interaction part. I don't know whether I'll have enough time, but I will like to go a little bit more in details in the later half. So this is actually the dipole Hamiltonian, and you can see this dipole moments. If you express it in terms of the spin states, you start seeing the physics, because this this part of the interaction will start like modifying the spin states, and that actually will couple into the electric field, or vice versa. The electric field also can be used for modifying the spin states. So there's a mutual coupling, and then the question is, in reading of the electric field, can you read the magnetic field information? So as a result, like if one is actually building a magnetometer in the lab as an experimentalist, there are like 3 steps one would think of. One is that one would like to first prepare the sensors. So actually state preparation, or optically pumping is the technical term for it. Then there's optical probing. This is where the light matter interaction comes in. And this matter is also like going through the magnetic field position. And then there's detection, where one needs to be very careful about what is the necessary noise budget and so on. So let's start with the first basic thing of optical pumping, which we already heard. So this is a very quick intro, but this actually will give us very quickly to get to a poor man's sensitivity calculation. So this is the deal that, for example, we can just think of a very simple spin-half atomic system, so we start with a equal distribution of atoms, and then come in with a sigma plus, so circularly polarized light, so that this actually goes from, like, it absorbs +1 momentum of the light field. But then there are decay rates that actually depends on the strength of the coupling, like if you think of Rabi frequencies quadratically, and then this different radiative decay rates. So they'll be decaying on this and that, but this state actually is not coupling because of selection rules. So this actually is dark to the optical field, and this will just keep accumulating the photons, basically, or the atoms. And so eventually, basically, this will empty out at the cost of the fact that the samples are spin polarized. So this is like having a very large spin. If you have managed to optically pump like n number of a million atoms, like it's like a spin that is like that long. And that is your starting point. And with that, actually, we can quickly think of have an overview of what a magnetometer essentially is doing in this simple model. So one thing to remember, and this is particularly important for experimentalists, because often we get stuck with the quantization axis. Sometimes we think that quantization axis is God-given, but actually quantization axis is your choice. And what looks like an eigenstate in one basis looks like a superposition in another basis. So for example, if a magnetic field is actually placed in an orthogonal direction, and we have spin polarized here, so these states which were in the X quantization axis now looks like a superposition in the Z quantization axis. And as a result, in the Z quantization axis, the magnetic interaction is very simple. It's just it just picks up the Z component of the spin. So basically here you can just plug in, and you can see that because of the spin SZ component plus half and minus half, these two will have two opposite phases. And now you can ask back that, this is the bright state, as in this is the state that actually interacts with the optical field. So what happens to the probability of occupation of that state. And interestingly, you just basically calculate the overlap, and you see that actually that's if that is your signal somehow, if that is what optical field is coupling to, there's an oscillation. And this is this famous Larmor precision, and this omega L is basically coming from the Hamiltonian, so it actually depends on the magnetic field. So if you can see this oscillation, and as we have heard in this school many times, that you can actually look at it in the frequency domain, but if you're like struggling for some reason in resources, you can actually real time measure this oscillation and calculate the magnetic field. So now comes the important question, that how well I am measuring the magnetic field. So what is my, so already we have heard this problem in very fundamental manner in terms of like a parameter estimation, Kramer-Rao bound and all that. But this is a experimentalist way of looking at it. And we don't talk about Kramer-Rao bound directly. We talk of signal to noise ratio. So signal we already talked about. So one way we can actually start thinking of this problem is that we are trying to detect a small signal, as in a small magnetic field. So we start with actually like polarizing the atoms in the, so MF is basically F, but in the X direction. And let's ask the question that in presence of a magnetic field, what happens to the state in a short time? Like how much the state is changing. And actually this is just simple Schrodinger's equation. You actually see that there's a change because of this dipolar magnetic dipole coupling, and this Fz is now trying to operate on this. And the same principle you need to convert back, but in this case, the operator, so this actually becomes just kind of, in this basis, this operator starts looking like raising and lowering, but this state cannot be raised any further. So this lowering starts acting on it, and it actually brings it down. And there's a factor here. This is like just simple harmonic oscillator like this, or angular momentum algebra. And then you recalculate, you ask that, okay, like, if I actually now ask, like, what is the spin projection on this direction? Because maybe my optical field, that is where it's coupling. So this is my signal. And you basically find, when you actually take the, between the same states, when you take the product, you actually see that that Larmor frequency is showing up, but also there is this delta t, because we are taking a very short time. So in a very, in this time scale, you see that this is actually increasing linearly. And then there's this F, which is coming from here. So this, for now on, like this calculation, I'll take a little more seriously and just put this delta t as tau. This is kind of the time over which the system is evolving. So, so now comes the noise. So how much noise I'm measuring? It's basically, since I'm measuring this operator, so I'm asking the question, what is the fluctuation? So actually you can just directly calculate from here, Fy square. It's a little bit of algebra in those states. And you basically find that the noise is square root of F over 2. But there's also an intuitive way of thinking about it, because this is inherently a quantum noise. And the best picture would be that, that actually we have polarized this large spin along the X direction. But what happens to the Y and Z components? Like ideally, classically, we would say, oh, they're not there. But quantum mechanically, there's a commutation relation. There's like first quantum 1. And immediately we know that that actually puts a uncertainty. So there are fluctuations. And this Fx is actually a very large number, n times the individual spins. So actually, like if it turns out, so there's a cloud around the spin, because like Fy and Fz are uncertain. So if this cloud is isotropic, which is kind of the case for the states I was showing, so some coherent spin states with isotropic fluctuations, then actually you'll see that this is just both are equal, and then this is like square root of F over 2. And remember that the signal was still going as F. So you might say that, oh, F goes as the number of atoms, so 10 to the power 6. So this 10 to the power 3, a large number, but your signal is still going as 10 to the power 6. But of course, there's a whole field, a very beautiful, amazing field of quantum metrology, where actually this is one of the target points, that can we prepare the atoms in a state where actually, at the cost of one of them here, I actually squeeze the other one. So there are like very interesting, like this twisting Hamiltonians and so on you can do to actually prepare a state which will actually, at least in one quadrature, will give you lesser fluctuations. So now the signal to noise. We have a signal expression, noise expression, and if we actually now divide the two, it's just like basic simple thing. You actually see that again, like the signal to noise is proportional to B, and also it depends on like the time basically the system has evolved. And this part basically that now this was all being done for a single spin case. If you actually like explicitly take care of the fact that there n number of atoms and m number of repetitions of the experiment, they are basically at this scale, they are essentially the same thing. And so you actually have these factors of square root of n and square root of n. So you can think on what we learned in this school that, this is coming because, Fisher information is additive. And that's where, you are basically adding these things up. But also you can just, from an experimentalist point of view, think of the fact that noise adds in quadrature and the signal just adds for each particle. So basically from there, you still get the square root of n and square root of n. So basically, what is then the sensitivity? What is the smallest magnetic field we can see? And that's actually sets when the signal and noise are equal. So this is kind of what happens in the lab, that the signal is trying to like raise its head above the noise float that you will kind of measure. So basically, roughly like when they're kind of equal, that is when you lose the signal to the noise, it gets buried. And so if you put that equality in that earlier signal, then, so basically what I'm saying is you are putting this equal to 1, and that gives you the minimum B that you can detect. And that actually is this. So you see that it depends on the number of atoms, it depends on the repetition, and also it depends on the time you're basically probing, or the state is evolving in presence of the magnetic field. But this is not the whole story. I was telling all this by actually suppressing the most important part, which is the fact that actually the spins are not isolated. They're interacting with the environment. They're interacting even with vacuum. So actually there's decay. So in reality, if you're actually doing this kind of a measurement where you actually first turn on a very strong field, you spin polarize, then reduce the strength of the field very quickly so that it's a probe, it's barely doing anything to the system, then you actually see that it's oscillating, but the oscillation is decaying. And then when you detect, you might not have anything to detect, basically. So as a result, one very important way to think of this is that you don't do all this, you actually just turn on the field, you think of steady state. So there's a decoherence part which is competing with the torque, this magnetic torque, and eventually it will reach steady state. If you like, I think Sai already did density matrix, so you can put the changes in density matrix to 0. But another way is to, again, poor man's way, you say that basically there will be a competition between the time scales. And when this, in fact, Amar earlier in one of his talk gave a very beautiful thing of how they will remain in phase up to the decoherence time. That's one way of thinking of the decoherence time. So you basically can put tau equal to 1 over gamma, the time scale over which the spin will decohere. So that is kind of the meaning of steady state, that's the average time that will emerge. And also, you can repeat the measurement. So, but each experiment is of the order of gamma, and if you are repeating m times, then your total time of measurement, which is a very, very important parameter for experimentalists, how long, I know how many days you have seen this Allen deviations and so on. So how many days I want to measure. So you would like to express finally this minimum magnetic field detectable in terms of the total time and this time, basically. So if you put all that, then actually this equation, if you see, like it was basically this, but now tau got replaced by gamma, it went upstairs, and then actually m got replaced by gamma times t. So there's a square root. So there's a square root of gamma, number of atoms, t total, and then there's this atomic constant. In this state?
Yeah.
Yeah, so that's what I'm coming to. Yeah, like, so you mean like when you're not looking at steady state, but kind of spin like ring down measurements. Yeah, in that case, you would like to have a very, very long tau. In fact, that becomes a major theme of the talk.
In this case, also you do some forbidden transition to get the tau larger.
I guess so, yeah. Like forbidden as in like if you can have a very low, but then the question is like how sensitive those things are to the magnetic field and so on. Yeah, but ideally, if you can choose one of those ytterbium transition where the gammas are months, but of course everything needs to be stable with that time scale. Do that, yeah.
I have one question. So how is noise defined here? So does it depend on sigma x square, sigma y square and sigma z square also?
Yeah, so this is
Yeah.
actually like, so you have spin polarized in the X direction, and you are actually doing a measurement where you are actually measuring the component along the Y direction, and you're looking at the component of the Y. And that is the whole idea, that you're looking at one quadrature in this measurement, right? Because JY or SY is, or FY is the one which is coupling. So you're looking at delta FY. And that is kind of the whole motivation for spin squeezing also, that you're not actually looking at the overall noise, but actually. And by the way, like in this poor man's way, what we have derived is kind of the most important equation in magnetometry. To a point, it has a name, and the name is very trivially uninteresting, but this is these bread and butter of entire field of magnetometry. It's called equation 1, and you will see you will see like papers and theoretical thesis written on analyzing equation 1. In fact, part of this derivation is actually from this paper, very beautiful paper, where actually they actually kind of try to explore many different kinds of, very dramatically different kinds of magnetometry scenarios, like all optical versus now we just looked at spin noise, and try to speculate that there might be something very universal about the spin equation 1, like somehow in very different measurements and very different noise dominations, you seem to be getting always the same equation. And why I'm saying very different noise domination. So let me, yeah, this is the question I think Subhadeep was asking, why not single shot? But I'll come to that. Yeah. I think the Zoom people will not hear it.
So in this context, this is the Faraday geometry of measurement.
This turns out to be like in this context, it's a very poor man. So you see, like, but this equation, like pretty much for all contexts, you will land up. If you're doing it carefully for the thing, you always land up with it.
So, for example, when you talk about spin noise, typically the magnetic field what you want to measure is in the perpendicular.
Oh, this is for the optical rotation detection, for not for the second order correlations.
Okay. So
no, not for the, or not for also nonlinear magnetometry.
Okay.
So you see that immediately, like, as an experimentalist, if I really want to hit the sensitivity limit, one thing I'll like to do is to reduce the spin relaxation time, make it small. And there's tremendous amount of literature. You can see this book or the other one I referred to. So you do it in many different ways, try to reduce the radiative, like decay by choosing ground state coherence. There are very interesting things, like, for example, if you have these atoms in the cell, they actually, you might spin polarize, but they're actually moving. For example, if they're room temperature, they're moving at like 300 meters per second. So they can collide with the walls and completely forget what was the spin polarization. It comes back as a random orientation, which is very bad for you because that reduces your large spin, and so on and so forth. There's transit time broadening, which is actually like, the atoms are flying off your actual optical field. So people put buffer gas, people put paraffin on the walls, so that the collisions are very smooth and nice, and so on. Of course, you would like to have the large increase in number of atoms that are interrogating. So people, they're routinely, the best magnetometers, the spin exchange relaxation free magnetometers are actually like, they go to like 10 to the 12, 10 to the 11 kind of number of atoms, and so on and so forth. If you integrate for long enough, provided your experiment is stable, that also takes you down. But that's not the whole story. Now, if you start making as an experimentalist, the noise budget, you see first and foremost, all this noise, just now what I talked about, the spin projection noise, the fact that, like there is an uncertainty always in F, Y, and Z is always there. But before that, even before seeing those things, your experiment needs to be stable. All the technical noises is well understood and taken in under control. And then this quantum noise sources come in, and we talked about the spin projection noise. But there's another one, which is actually coming from the detection, which is the photon shot noise. And that's basically, again, exactly the same way we can think of this, that we are actually, what is this photon shot noise coming in these measurements? We are actually kind of trying to see the rotation of the polarization, for example, because of this effectively like Fy component is coupling. So if I'm actually coming in with a X polarized light, there will be some component in this direction. I would like to understand, and this can be understood exactly in the spin language by thinking of this quantities that you can measure. So for example, this quantity is actually the number of photons you set polarizers in the X direction and then Y direction and take the difference. Similarly, this is you set polarizers at 45 degree, and this is like some quarter wave plate, and then half wave plate, and then polarizers. So these are like Stokes vector, but interestingly, they also have a similar algebra. And the whole physics of this uncertainty comes in. So, for example, if you have a fully X-polarized light, there's still kind of a uncertainty cloud around Y and Z, basically. And again, like if you actually somehow have a coherent state such that these fluctuations are exactly equal, you see that that actually goes as square root of your Stokes vector average, which is the number of photons in the X direction. So that's like square root of the number of photons. And again, there's a direction which has not been, like, if I'm not mistaken, has not been very successful, but people do have tried to actually spin squeeze in the optical field, and again the same physics. You can actually, like, since you're detecting one quadrature, you can actually try to squeeze, and that takes in the quantum metrology. And you can actually right away see that what is the relative angular fluctuation. It's basically this, if you're measuring like in an orthogonal direction, delta S2 over S1, and this is basically going as a square root of the number of photons. And if I relate back this to the number of atoms, then actually you see that this number of photons are basically the number of atoms which are you're sensing times the scattering rate in the direction of the detector. So if you have directed scattering, well and good, but otherwise you are basically collecting a small little solid angle over 4 pi and then observation time. So this is basically this number of atoms in observation time. T observation will scatter these many photons basically. And so again, this noise is also set by your this thing. And then finally, there is this back action noise, because you are actually using an optical field, and no matter how weak, there's always basically a coupling back to the atoms, and it's trying to modify the atoms. For example, there's a very nice little thing you can, for reference, look at Cohen-Tanouji's atom photon interaction. First chapter, it goes that suppose you have a state which is coupled to a continuum, so it picks up a line width. This usually we call spontaneous emission. But then you have a fully stable state, like let's say like no coupling to anything, but it's only coupled to the excited state. Actually, what will happen to this state? It will have a dispersive, like it will have an effect on its energy, and it will also pick up a scattering rate. So if you are detuned slightly, then the shift in the energy basically goes quadratically with your electric field strength, and the scattering rate actually, so scattering rate means this will actually, through this coupling, it will start seeing this external thing, so it will pick up a line width. And so you see that as a result, for example, the shift itself, you can right away see that this shift is actually shifting the energy level, but that's exactly what the magnetic field is doing. So now this actually starts looking like a pseudo-magnetic field, besides the fact that your things are getting scattered and so on. So this actually, like there are beautiful schemes to evade this kind of back actions in different ways. And you can also start thinking of it, that how you can maybe balance with some other directions and so on, and or maybe increase delta so much that actually this stops playing a significant role, and you're basically go into this quantum QND regime or quantum non-demolition regime, which just basically, in our terms, means that it's not really perturbing the atoms that much, but nevertheless, you're energy shift. Did I get it? Light shift. This is basically light shift. I'm just talking light shift and scattering. So this is like basically delta plus I gamma, mod square. So like their delta cancels out. Yeah. So basically now, how do I think of it? Like like this is a simpler picture, that if these noise sources are independent, and I have already told you, there is back action noise, so they are not really independent one. So think through carefully. But in the zeroth approximation, if these noise sources are independent. There's a very important lesson for experimentalists that, noises, independent noises add in quadrature. So if already, this is a lab law, all starting experimentalist students should know that if one noise is dominating, for example, if your technical noise is dominating, there's no point in thinking about this. Similarly, like most standard magnetometers are actually operate in a regime which is actually dominated by the spin projection noise. There's a short noise and back action noise, but what I'll be talking later is actually this short noise regime actually. So that is the part. I think there were questions, so let me move on. So I'll now switch gear and talk of another part of atomic physics, which is basically atomic memories. And in atomic memories, the basic idea is kind of straightforward, that this is kind of a flow in time. So you have an optical pulse which comes and interacts with the atoms, but then the interaction is such that it's kind of an adiabatic rotation with some unitary, actually. So it's a unitary evolution, not a projective measurement of any kind, where this photon adiabatically gets converted into spin states, and then for a while it evolves, and then you take it out, right? So this is the time when actually the optical field is stored, right? And these are different fields. So I should not have had the magnetometer here. That is the point I will try to make. But otherwise, there's a different field where you are actually, this is related to quantum communication and so on, where you are actually trying to store photonic states in an atomic medium for a finite amount of time, because photons are always traveling. So, and then you release it back. So in a deterministic manner. But then suppose somehow you can actually, I'll come a little, if I have time, I'll come a little bit more details on this memory. But suppose somehow when you stored the photons, the atoms actually also are subjected to a magnetic field. And when you are retrieving the photon, the atoms actually spit out whatever they learned during that time about the magnetic field back to the photons, right? So then how would the sensitivity scale? So you see that there are two very important parameters if you talk to quantum memory or atomic memory people in quantum communications. They'll always talk about the storage efficiency, like how many photons actually are getting stored in the atom, and a recovery efficiency out of the number of the number of atoms which are storing the photons, how many photons you are actually getting. So, and these are both very important. So for example, this is basically the number of recovered photons over the number of recovered atoms. And like if you actually see that this is a field which is like tremendous progress is going on. For example, like 2021, 22, people have reported this storage efficiency to 90%. Like if you're coming with 100 photons, 90 of them you're storing, and they're recovering. Actually, this is a result which was earlier, very early on from my postdoc lab, but now this number has been pushed to 0.7 or 0.8. So out of 100 photons, you're storing 70 or recovering. So actually you can see that, that suppose, like as I'm saying, that suppose this is actually has the information of the magnetic field, then your number of photons you're actually recovering is what is setting the sensitivity, the phase sensitivity. And now it is not really the scattering rate and so on, but it's actually the number of atoms times this recovery efficiency, which is actually a quantity which in some cases becomes geometric, but like it is something different than scatter, like 4 pi solid angle scattering. Instead, like usually these are like very directed emissions and so on. So if you even have moderate, like the experiments I'll be talking about, even if you have very modest kind of number of photons, for example, like atoms, for example, 10 to the power 7, and if your recovery is 0.1 or something, you're still actually like you become like photon shot noise dominated, and also you are actually in a single shot, you have still enough number of photons to actually have a signal that you can actually play with. And so with that, let me at least outline the points I'll try to make of maybe the advantages of an atomic memory magnetometer if this kind of a process happens is so firstly, you see this point I was trying to make, that this is a thing that has been a lot of effort is going on. So just by increasing the recovery efficiency, one can very quickly come to standard quantum limit. But also, since now we are actually talking of back to this kind of a free evolution of storage. So now this actually becomes this tau now becomes a function of storage time. Remember, this is the earlier equation, just before equation 1. So this is going as 1 over tau, but this tau is now the storage memory time. And actually, this is another tremendous drive from the field of quantum communications or quantum memories, where actually people have even taken it to seconds or even minutes, like minutes of storage time. So actually you can have a very, very large number here. So, and finally, a point I'll try to make for the technical people in the audience, that sensitivity is not the only thing practical magnetometers are of interest, because also there's something called a dynamic range, that over what range of magnetic fields it works. And it turns out that, a huge goal in the field is kind of to make this line widths very narrow, which basically means that the magnetic resonance is happening over a very small range of the magnetic field. So basically, you might be measuring femtotesla of magnetic field, but if you put like more than picotesla, on average, you are already out of the resonance and you don't detect anything. And so basically, like even in Earth's magnetic field, unless you're nulling everything down, you don't detect much, right? But here, actually, this memory, very interestingly, this is also a set of studies we have also been studying, where actually it turns out that there's a regime called Otler-Towns regime, where actually it's kind of interesting, but there also this memory works very well, at least in this approximation. And in this Otler-Towns regime, the line width becomes very large. So actually, if such a thing you can realize, then actually you can actually have a large dynamic range. So with that, let me now actually talk a little more about light matter interaction and quantum coherence and memory. Yeah, I don't know. This part, I actually had a little bit more details as a tutorial, but maybe I might not have enough time. So basically, the idea behind quantum memory, and I'm really switching gears. So for a while, don't think of magnetometers. Just think of this problem of actually you have a photon, a traveling photon, basically. So effectively, a two-level system, whichever basis you choose. And how can you map it to an atom, essentially to a two-level system? And ideally, one would say that, this is a simple and easy problem because it's basically one two-level to the other two-level, but you need to figure out the interaction well. I'll skip this part. One little thing is, I think like Sai might have already talked about, this is also a very atomic physics thing, that I'll be talking about some density matrix, which is a description of the atoms here. And often I'll be like, like the standard things are the diagonal terms we call population, and the off-diagonal terms basically we call coherence. So whenever I'll be talking about atomic coherence, I'll basically mean like off-diagonal terms of the density. So now you see this mapping of this atom. So you can actually see that like this coherent oscillation, Rabi oscillation. So this is like, I don't need to go through this. Just this coupling will actually make this population oscillate. But then again, the fact that the systems are not independent, they actually interact with vacuum and so on. So as a result, in reality, what will happen exactly the same similar physics I was talking about, that you will actually see decay. And this is the problem, that even if you actually make this system like some sort of a coherent oscillation, you will basically see after a while the system is decaying out. And if you actually look at the spectroscopic signature, you will see that it kind of looks like a boring absorption peak with a width which is basically set by this, and these oscillations and so on are gone very quickly before you can actually see them. So there is a very, very nice physics, almost 30 years old, where people realize that, firstly, this kind of a mapping, if you can have two very stable states, for example, two ground states, you can actually do this mapping of the photonic states very well. So somehow you need to eliminate this excited state. And how can you do that? It's a very clever trick. So it's the same dipole Hamiltonian. You see that basically this is the energy of the, this is the decay of the excited state. So this is a non-Hermitian Hamiltonian, but if you're not comfortable, don't think of it now. But basically this is what is happening. So for example, this term takes the atom from the ground state to the excited state. And this actually couples this 2 and 3, right? Like, so this is the Hamiltonian. And actually to see, so there are two optical fields. One is a strong one, one is a weak one. And you can right away, without solving anything, you see that this excited state, which is kind of the bad state, it has a decay, it actually couples in a very specific way to the ground state manifold. You see that the coupling coefficients are actually set by this coupling constants. Right? It immediately tells us from very basic quantum mechanics that if this is the state it's coupling to, there ought to be a state which is orthogonal to that, some superposition of these two, which it will not couple to. if you basically you can just right away construct a orthogonal state by putting this coefficient on this and that coefficient on that conjugate, and you see that if the Hamiltonian now operates, it's not going to do anything because it was supposed to take excited state from this state, right? And this is really the physics behind this thing, what is called often called electromagnetically induced transparency, that actually once that happens, and you suppose you have these atoms in this state, but you turn on both these fields, very quickly the system will actually go into, you can think again change basis of the ground state. So actually you can think of this as the dark state basis and the bright state basis. Exactly the earlier what I was talking about, but in this case, basically the bright state is what is coupling to and dumping atoms in the dark state being a superposition of these two. So and these are like very long lived, you see, and suddenly you are actually creating a qubit basically. And the most important thing here, which is often missed in EIT, because often people think that if you have a transparency dip, that's enough, that the probe is suddenly going through. But the main physics is the fact that since you are actually eliminating completely the excited state, which is what is responsible for spontaneous scattering. So even in principle, you do not have any spontaneous scattering. And this actually works magically. Like if everything is right, in fact, you can precisely in this system store exactly 1 photon and get precisely back 1 photon without a single scattered photon at all. And if you think of like how important, how like all this light is basically spontaneous scattering, and in that you are actually exactly getting 1 photon without any scattering. And this is the physics behind that, you are eliminating the excited state. So how the data looks like, it's basically, so exactly what I was saying, that as a spectroscopist, what you will see, an absorption peak when you are seeing a 2-level system. But now when you actually do this clever trick, you send in a strong beam, you will see actually suddenly this probe is going fully transparent because, there's basically like, this dark state is where the atoms are getting shelved into. Right, so this is actually like in some ways, if you get it nicely to 0, this is really a superposition of the fact, like a signature of the fact that you have created a quantum superposition control, like a qubit in the lab. And this is one thing that we have been looking at very closely, and you will see that many of these things that we are working actually helped us in understanding this magnetometer. So for example, one of the questions we asked, and this part I just included because I think there are students who actually are studying this kind of physics. So for example, you can ask that this is spectroscopy. This is actually like seeing temporal dynamics, but then integrating over like in principle, like very, very long time. Can we actually real time see this creation of this, and that too in a very dirty system? Like this is actually from the lab, hot atomic vapor where things are moving at 300 meters per second. And there we actually started doing an experiment where we started like turning on and off this strong field in real time. And what we saw, for example, this is actually a trace where you are actually seeing the probe light. At this point, we turn on this other field. This EIT physics comes in, superpositions are created. It actually shoots up. There are reasons for that. It turns out quantum superposition happens earlier than optical pumping, but then eventually it reaches a steady state for a while. And then at some point when we turn it off, there's a sudden fall. And we started looking at it closer and closer. And what we realized, it's kind of very cool. You can see this in the oscilloscope, and you see there's a theory, like basically theory as in like the simulations of this thing, which fits very well, explains everything. Otherwise, an experimentalist intuition will be, oh, you are having some detector overshooting and so on. But this is exactly what you expect. All these curves you can explain. And this fall is precisely a kind of becomes a measure of superposition, basically, in the system. So it becomes a quantifier. So we use this, for example, to do, like we have been studying this for a while, but one of the things we did is actually to start increasing the field strengths. And what happens at some point, there are this dark and bright states. This is the EIT physics, but as you start increasing the field strength of the control, at some point, this state starts hybridizing with the excited state, and kind of a different physics sets in, where you do not really have exactly a ground state, but there are this excited state superpositions. And then this is the regime which is called the Otlet towns. And there actually you see, so these are actually measurements. It looks like spectrum, but these are actually measurements done by just measuring this fall height. and then putting a magnetic field and changing it, and you see basically that, like as you move on, this actually peak broadens out. And this physics, this only for this physics and the fact that several people are working on this kind of systems here, I included this because this part actually will play an important role when I'll talk, if I have time to talk dynamic. So yeah, so this is, I think I'll skip this part. But now let me come back to the actual main story, and that is actually this atomic memory, and this we do in a cold, very simple magneto-optic trap. You see, it's a like ghetto and very small setup. It's a tiny little glass cell here, which probably you cannot see. These are coils, and when everything is right, we actually trap kind of a cigar-shaped cloud. So it has a large kind of optical depth in one direction. It's 50 microkelvin is what we estimated, but then, I'll talk about like state preparation. So we actually trap the atoms here, bring them down, spin polarize in different states. You can actually put them all here. You can put them here and there, and so on and so forth. You can play these games provided you know how to probe them to know you have the right states. And all this actually costs heating. Eventually, this memory I'll talk about goes up to a temperature of 120 microkelvin. So yeah, this is a side view. So let's now come. This is just technology, but how a typical experiments look like. And I'm starting with something very simple. Suppose an optical field just falls on the detector. There is nothing, but this is a pulse of light. So this is how actually there's an experimental trace from an oscilloscope in the lab. You see a pulse. Absolutely trivial, but now you trap these atoms, and the moment you trap this pulse completely gets absorbed, right? So, and then you play this game, you actually turn on the second beam, and you actually see this completely absorbed pulse. Now you have turned on, but it's a pulse, control pulse, and you see that this comes up, and this is basically the system is getting transparent, but this transparency is very special because, like it's actually becoming transparent because there is a off-diagonal term of the density matrix or a coherence being created, and that's a ground state coherence. So you have actually created a qubit. So now, like actually, if you think of the whole system together, like the optical field and the state and the coherence, you can write it in a wave function, but also you can write it in terms of operators. But basically, this grand wave function actually has partially this optical field and partially this coherence. That is a very simple way. And this kind of a total state, which is neither an atom nor a optical field, but a superposition, like a combination of the two, coherent superposition, is usually called a polariton. Also in condensed matter physics, here we call it dark state polariton because of the dark state physics. And basically the interesting thing is that these coefficients you can control in the lab. Like so cosine theta you can ramp up to 1 or 0 depending on your strength of your field, and similarly for this this coefficient. So you can actually change them, and let's start changing them. For example, like this was the light that was coming out. Suppose we stop the control field earlier. You see that this was actually trying to come out, but now we have turned off the control field. That support is not there, so it's now getting absorbed. But the interesting thing is that this absorption actually, there's a coherent superposition. So at a later time, if you wait for a time and then turn it back on, you see that this coherence is now adiabatically rotated and is converted back into omega p, and that's what we retrieve. And kind of this, so this is the a direct experimental thing for what I was earlier talking about in the cartoon, that one might be concerned about like storage efficiency, how much you are actually storing and how much you are controlling. It turns out this coupling coefficient actually scales both as the number of atoms out of many other things actually. So now you can see that we are almost there. I just talked about the quantum memory, which is basically a giant wave function of the probe and the coherence and the coefficients we can control in the lab. But you can see that, like, suppose I put a magnetic field now because I'm interested in making a magnetometer. You see that basically there will be a delta, like there will be a shift in energy, but that energy will appear in this coherence as a phase. Overall phase. If I convert it back to the probe, that will be an overall phase on the probe. But I don't detect like electric fields, but we'll detect intensity and the phase is gone. So this is not really sensitive to magnetic fields. So somehow we need to make it phase sensitive. And that's the part where actually, if you kind of extend this such that, like you prepare the atoms, for example, here, and actually create a situation where actually you kind of, in a small field limit, you create two such polaritons. Then you see that if you put a magnetic field, this might pick up a phase which is opposite to that. And as a result, when you retrieve this, optical fields will interfere, and you can actually start retrieving the magnetic. So yeah, so that's kind of like, so what I just now said is what is here, that there are like two polaritons. Actually, if things are right, I'll like, we are experimentalists, so I'll give evidence that this is kind of the physics going on. So you can actually put this together, and you see that then what you retrieve is actually a superposition of these coherences, where this phases, of course, depends on the phase difference between the optical fields, but also the phase that might be purely atomic on the thing. So you can pick up magnetic fields and so on. So this is an experiment. Now we have like shifted to this experiment, where actually you see there are like two control fields. Atoms are here, and this is the weak proof field, which is resonant here. This is an experimental trace, and you see that we are actually storing and retrieving at different times. So each of these are like separate experiments, and this is kind of the delayed waiting time. And as I was saying that, here it's purely like, when it's interacting, it's atomic at photonic. When we shut down, this is the interesting part. Here it's purely atomic, but it's coherently storing the optical information. And then when we retrieve back, it's rotated back into a purely photonic state. But now the question is, I might have, yeah. Yeah, okay, this is there. So now the question is like, is it really actually having a superposition? Because this curve looked very similar. So, so as a result, if there's a superposition, something different will happen as opposed to usual memory if you put a magnetic field. And that is what we do here. We actually put a magnetic field, and we see that now this retrieved light has additional oscillations. So you see that it's kind of going up and down, and depending on the strength of the magnetic field. So basically, you see that these are like interfering, coherently interfering, and there's effectively a relative field. So and just kind of to mention this, which if I have time, I'll come to that. But actually, this is not the only configuration where it works. You can actually have the opposite configuration also, where you can actually spin polarize the samples in these two things and have a strong control field here, and you can still see oscillations basically. So this is what I had in the earlier figure. You see that this is what it meant by the quantum memory magnetometer. This is actually storing, this is retrieving, and you see this oscillation. So, and this is, this is like, we actually size there with, we actually use this to do demonstrate quantum synchronization for the first time, where actually you see this beautiful interference phases with respect to this, control and the optical phase and the magnetic field phase, but that's a different story. I'll not get into. So now comes to the fact that how sensitive is this magnetometer? It's just like exactly this earlier thing I was saying, that the first part is your signal. Signal should depend on magnetic field, the very early introduction. But now the question is like, what is your noise? What's happening? So you see that basically the magnetic field information is there in the fact that the intensity has become phase dependent. So we need to know the noise. We need to know the this thing. So one of the first things is, like, is it even a linear magnetometer? So here we start actually looking at whether there's any distortion from sinusoidal oscillations. So we just increase the magnetic field. Actually, we go higher than this, but this is over a Gauss. You see, like, this is what I was first saying, that, there are these issues that you are usually limited to like very small magnetic fields. But here you see that we actually increase magnetic field, and we also start increasing probe power. And we see that they fit very nicely to like sinusoidal oscillation. And the reason we were increasing probe power is because of the fact that this is actually the same recovered intensity as a function of number of atoms. And here something is very interesting is that, what we started seeing is actually there's a quadratic scaling, like basically like, like this intensity starts scaling as n squared. So this is what the recovery looks like. It depends on many things. There's a sinusoidal oscillation. This delta actually is where the magnetic field information is, and there's an n squared scaling. Believe it or not, this n squared scaling right away fooled us for 6 months or 8 months, because, like you can see that if this is n square scaling, and if you are short noise limited, then basically the noise is scaling as square root of I. So this noise scales as n, and the signal, which is del I del phi, that scales as n squared. So suddenly, you have a sensitivity scaling, which actually goes as 1 over n. It looks like Heisenberg limit. And we thought, oh, there must be something very interesting going on, Dickey superradiant-like effects. Maybe the atoms are being driven to some sort of a thing. So we started making a theory of Dickey superradiance to actually see these things. But it turns out, I already gave that argument that this is not the right way of thinking, very simple, stupid, silly mistake. Actually, one should really think in terms of the recovery efficiency, because what is sensing are the number of atoms. So one should not think from the beginning to the end, but one should start from the atoms already stored and they start sensing. And then the question is, how out of the number of sensors, how many you actually convert back to photons? It takes me 30 seconds to say this, but it took us 6-7 months to understand, or even more actually, this simple fact. But basically, if you look at the recovery efficiency, that scaling is linear actually. So number of atoms. This is number of atoms. So this is the number. This is basically like so. So the this is the number of atoms that we characterize in the magneto-optic trap in the same interaction region, and that is what we change by either shelving and bringing down from shelve or through getters. But the actual number of atoms one can characterize from photons, which is not very far from this, basically. So these are actually the number of atoms which we are changing in there, and this is quadratic scaling now. But basically, you see that the sensitivity is still 1 over square root of n times recovery efficiency, what I initially was saying. This is quadratic scaling, but yeah, but we can discuss more on this. Yeah. So, this is quadratic scaling in terms of the input intensity. Yeah. But intensity, like here, like one needs to like see what are the sensing. So if you actually see the number of photons that one is recovering, that is never larger than the number of atoms. So basically, n photon is total number of sensors times the recovery efficiency, which is never larger than 1. The best numbers are 0.7 and so on. So that is the thing. So if you have recovery efficiency close to 1, you hit very quickly. You come very easily and quickly by using the whole quantum memory physics to come to SQL. But yeah. They are coherent, by the way. This superposition, otherwise you would not have seen superposition. You see the coherences are actually interfering. If they were incoherent, this would be like 2 independent samples. And there you would not have seen this. We can discuss this. Yeah, I think I'm out of time. Yeah, so basically then it's a question of like actually now doing delta I, and it's this adiabatic rotation, but we have done carefully the measurements both in a very low photon number regime, trying to see what exactly the the noise that we are measuring, and whether we are seeing contribution from atom noise or whether it's short noise limited. So you can see this is again like increasing number of atoms with like number of photons. These are like very low number photons. But when we actually look at it as a function of number of atoms, the photon fluctuation, characterized from this, actually you see that this is linear. So basically, like we are I would not say short noise, but at least it's linear scaling. And the same is true in the high power regime, where the measurements are very different. You're looking at spectrum, and you're looking at actually the increasing. So we are at short noise limited detection, and there also you actually see kind of a linear scaling. So given that, actually, so this is the sensitivity plot, and you actually see, like these are our measurements, and you see that as we increase the number of atoms, this comes down. We are basically around like 10 to the power 6, 10 to the 7 atoms. This is SQL. This is one configuration. We are like a few dB away from the SQL. And here with this magnetometer, within a time scale of like about 750 nanoseconds and so on, single shot, we are actually coming down to a sensitivity of picotesla, basically. So, but interestingly, if I even take moderate timescales by changing configuration, for example, so we are somewhere here, there's another set of measurements. But if, for example, even if I take a storage time of 2 seconds, which is like far more modest than what this quantum memory people have achieved of minutes, you are already starting to hit attotest, basically. And that's kind of has become suddenly we thought that this is beyond, a little beyond like just like playing and trying to see what is sensitivity, but this might have something more interesting and serious. So there's this whole dynamic range and outlet towns, so one way to understand it is to actually, so these experiments is a theory, so you can actually recreate the states. You can do a tomography kind of a thing. And for this two, it turns out that like actually you can think of the magnetometer in these two configurations, and you can ask like, where is the, which one is good or bad? It turns out that two different things have different effects. For example, you can actually see that here, the atoms are in the middle. There are this control fields. There are two of these control fields actually pushing this. So whatever that light shift effect I was saying, that effect will be actually magnified for this. So there will be more back action noise. And that is still there. Whereas in this case, actually the atoms are being pushed by weaker fields, So one way you can think of it are actually like plotting these things in a phase space, this Husumi cube, which I can actually visualize in a 3D, on the surface of a 3D sphere. For example, this state, actually, before you turn on the control and the probe, it actually looks like a isotropic thing along the equator, whereas this state actually looks like the two poles are occupied. And when you store the light, this state gets localized, and then with magnetic field, it starts precessing. And the same here, this polar states actually just gets tilted and then starts like wobbling around, right? But because of the light shift, one just like basically one spreads out more. And as you start increasing magnetic field more and more, basically one of them kind of washes out. That is one way of understanding the dynamic range. So these are the plots, so this is one scenario here. Which actually here you see that we are actually going up to this one actually has a more flatter profile, and this is done at a higher probe power. So there's a broadening. So Bmax is this thing. So also there's this quantity visibility you can talk about, which turns out to be a nice quantity, which we realized in a kind of a nice way that if you look at the fringe visibility, you can characterize the sensitivity as well as the dynamic range. In fact, Kasturi's talk today morning had this 1/c contrast, which is kind of the same thing. So that's one interesting thing. And then you can actually ask what is the Bmax over what fraction you're doing. So we are actually basically that factor is 10⁷ or so for this system. And then you can do it in the other configuration. And there you see you hit better sensitivity, but then it kind of sharply changes. And basically, you have a smaller Bmax, but you actually have a sensitivity here, which comes down to like 3.8 picotesla. And these are all in a measurement time of that, basically. So let me just conclude now. And sorry for rushing this part, but we have another week. And if you have questions, the student, it would be nice to discuss. So basically, this is what I was talking about. That in fact, Sai, this is the point I was trying to make earlier in that introduction, that basically your phase sensitivity goes as the number of photons. This factor of 2 should not have been there, but that number of photons are the number of photons recovered from your memory, and that's basically the number of atoms which are storing it times the recovery efficiency. And if you see it this way, this factor is never larger than 1. So when it's 1, you are hitting the standard quantum limit, 1/square root of. But then the way we were seeing, and we are like really, but we learned a lot of things on quantum metrology in the process 1/n scaling, but nothing ever gets to waste. But nevertheless, we are thinking that basically, that there's actually a 1/n scaling, which is still like, if you increase, there's a quadratic increase in the intensity, which might be very interesting when one is struggling to get good signals. So and then the sensitivity scales now as this inverse of storage time. And as I was arguing that, the storage time technology, people have been working like relentlessly for last 15 years dedicated to increase the storage time. I was showing very moderate storage times of 750 nanoseconds, 1 microsecond. We have in this memory, in this configuration, we have about a 1.5 microseconds. But if one actually pushes this to, like milliseconds or seconds, already one is like, it's 10 seconds is like really good. And then there's this Otler-Towns physics, which also, along with the sensitivity, as opposed to surf and so on, actually gives a wide range. Most importantly, it should operate within Earth's magnetic field. So just kind of, again, making these points in a different way. So this is dominated by short noise is an official conclusion. Sensitivity scales inversely with the storage time. Then, there's this double quantum coherence. So the double quantum coherence magnetometry, in the sense we have already discussed, I think Amar also earlier talked about, and others also talked about, that this kind of a situation has other inherent advantages, because you're kind of taking the difference of the phases. So a lot of common mode thing drops out, which people have done in magnetometry earlier as well. In this case, actually, it becomes an advantage. And then, and one can think also of light shifts canceling and so on. So one very, very big advantage here is that this when one is recovering, as opposed to like Ramsey and so on, where you kind of let the atoms precess in the dark, but then you kind of flip the atoms back so that they are in, like, the coherence is mapped to population, but then the measurement is always a fluorescence measurement, and there it actually, you need to send in a lot of photons, and you're collecting a very small amount in your detector solid angle. Here, actually, there's a phase matching condition. It's exactly this physics, that same photon you are storing at the single level exactly comes back in the same mode. So if you are doing it with many photons, it's an extremely directed emission directly towards your detector. That actually is extremely advantageous, because like many of these things you can actually bring down. Of course, the fact that there's a dark period, which is always the case with any kind of this dark things, that you in principle also during this dark phase you do not have a weak probe light. So during this phase, actually one doesn't have any back action noise, basically. So if you actually have this time scale to be 2 seconds or 10 seconds, in fact, this basically this starts looking like back action evading, because this little 100 nanosecond, 200 nanosecond light shifts are extremely small, basically. And this might be a alternative way, as opposed to this what people would do of increasing detuning and so on. Large dynamic range. And then large sensitivity. Like these two are actually two different configurations, but I'm quoting the best number. So with that, I'll stop. Sorry. So this is a group. This is a large part of this, some part of this is Pratik's thesis. We also work on some graphene optomechanical resonators and so on. So Arnab just finished his thesis, like just submitted his thesis, and then and Atish, Shubham and Gautam are here. They are also very strongly, deeply involved in this project. So if you have questions, and if you're not finding me for the students, please you can talk to them with anything. And there's Javed and Jyoti also working on the graphene mechanics experiment. So with that, it will be great to take questions. I finished.
Okay. So since it's already 7 o'clock, are there any short questions from the students first? Any question from the students?
Sir, you have, for your case, it's the photon number, what you are caring about, the recovery of the photon numbers.
Yeah, so you see, we have about 1 million or 10 to the 7 atoms. So our photon numbers, we are detecting at 10 to the 6.
Yes,
10 to the 5 maybe. So we have, our recovery is not that great. It's like not even 0.1, it's lower.
But is there, you talked about the phase at the last part. Is there, it's important that the photon.
The phase is where all the information is.
Yes.
Yeah, but I have, I think, everything here. So this phase you're talking about?
So I am talking about that which photon is coming. That photon state is captured in the atoms. Then is the photon, the same photon is same type of state is emitted in the photon that is recovered?
Ideally, yes, exactly. Yeah.
Yes.
Like as in, like, like when you're talking of a single photon, you need to be careful, like what you mean by the phase. So for example, if you somehow put a single photon in a polarization superposition, right, you can actually store it. In fact, like earlier during my postdoc, we actually showed, we have a paper where we actually like exactly precisely stored 1 photon and got out 1 photon and did a state tomography of that photon, recovered photon, and compared it with the initial photon. And basically, you get like fidelities of like more than 90%, 94%, 95%. So it's extremely well, it works out. It was actually the experiment done in Vladan Vulettich's lab at MIT. So you can actually look at that. It was a kind of it was in a PRL paper of 2009. I do not have the. You can actually see like the efficient, like the fidelities are extremely high. You know, of the process.
Any other, let's say, short question?
Hello, sir. Sir, you explained electromagnetically induced transparency. And when you wrote the Hamiltonian, there was a term containing imaginary number I. So what does it physically mean?
Physically means like it just tells you that there's a decoherence. So also, if you noticed in the same spirit, when I wrote down the master equation, the evolution of there was a Lindblad term. No? So that's basically like, you know, if I want to like so in some approximations, if the rate of excitations are low and so on, and if I'm not comfortable as an experimentalist to work with density matrix, because I cannot think much more. So I would like to go into a wave function picture, and there it turns out at the cost of making the Hamiltonian non-Hermitian, you can actually like, and then just like boldly do calculations, and you will see your wave functions will pick up like decays, and eventually everything kind of works out, provided your field strengths are not too high, so that you are not having to make what are called just jumps and so. But of course, there are like real experts sitting here, all the theorists. Yesterday, Sai was saying much more intuitions, and you can discuss exactly how it's done and so on.
But here, anyway, we work with high pump power, right?
No, this is for the weak probe limit.
Oh, okay.
So this works out very well. Actually, like for us experimentally, it works out very well for intuitions. So I would strongly recommend that you should do. You should anyways try this out. But if you have this high power problem, you will have to think of that non-Hermitian Hamiltonian and a simulation where every now and then you are kind of randomly choosing whether the atom should make a jump from the excited state to the ground state, and still you're in a wave function picture. And the stochastic trajectory kind of gives exactly the same result you expect from master equation. So it has an exact mapping, and for us also it's a poor man's way of thinking of decay and Hamiltonian.
Okay, so then I request, I'm sure there are many more questions. So let's, I mean, he's also here. So is it okay, please?
Yeah, absolutely.
So let's discuss
The whole week
outside.
I'll be here.
Yeah, yeah.
One
so
of the
please
last person to
discuss.
leave on Saturday.
Yeah. Okay, so now, on behalf of the organizers.
Oh,
okay. So the elephant. Okay, thank you, Saikat.
Thank you.